Start the recording. Okay, I got too many assistants in here. I might have to throw you guys out. All right, so we introduced the topic of solubility in complex ions in chapter 16 last week on Thursday. Now we're going to do a little review and exam 5 on that chapter. All right, everybody out. Go on. Out. Out. No, you can stay. All right, sorry for the interruption. So the exam 5 will be on Thursday. And also on that day, we'll jump into the next chapter, 17, which is on spontaneity. We'll get to that later. Okay. So first off, are there any specific issues that need to be tackled in this particular chapter before we just run through some of the problems? Okay, if not, okay, so solubility. First topic in this chapter. Actually, solubility is an extension of our equilibrium study. Only solubility has some compound which is a solid and is in equilibrium with the aqueous ions that are produced from the solution of that solid. Now I've written this one with just, actually, that could be any charge, that could be any charge. And the M and X are the number of atoms of each element that define that solid. And in fact, they don't have to be elements. They can be polyatomic ions. Right? So this one could be that's the only one it could be that we've studied. This one could be almost anything. It could be chlorate. It could be chromate. Or it could be any of the elements. It could be a halogen. This could be any metal that forms a solid in solution, like silver. We've studied that one. So the key to the solubility equilibrium problem is to recognize that solids don't enter the calculation. Let's use a real example. So if we have this solid and we introduce it into pure water, then it would dissociate to a very small amount into these two ions, right? So then our expression for the equilibrium constant for this reaction would be just these two concentrations times one another. Because solids are never part of the equilibrium expression. So that's why we call it solubility product. Okay, now we can go to some problems. And let's see, if we start with number one, is that a good place to start? I want to start slow and pick up speed as we go. Okay. Number one, we're given this compound, and we're also given the solubility product for that compound, which is 1.52 times 10 to the minus 3. Let's take that out. In keeping with our equilibrium expressions, don't have units. Okay, so what would this produce? If that's written correctly, we know that all halogens are a -1 charge, so that means this one has to be a 2+ charge. So we have that and that in aqueous solution. Then the expression, the solubility product, would be this one times that one. But this one would have to be raised to the second power because of its coefficient. So there's our expression. And what we're looking for is the molar solubility. All right, so you need, let's do it the long way first, so we can prove to ourselves again that the shortcut works. All right, so if we have this expression, we're going to have an initial concentration, a change, and an equilibrium. Well, the initial concentration here doesn't matter really, but for solubility purposes, we're going to lose some of this. Okay? And it's going to show up over here as one of those because there's 0 to start with, and 2 of these. Right? Okay. So we look to see that we've chosen our unknown value, the S, in such terms that when we solve it, the solution for S is the answer. And in this case, it will be, because this says how much of that dissolves. And of course, these are concentration values. So we have, we don't need a value here because for equilibrium expression, the only thing that counts are the soluble components, right? So we don't need anything there. We just need these two to fit into that expression. Okay? So we have that value and that value. All right, so if we put those two values in there, we get, just make a little room here, we get an expression where this is equal to that times that squared. Right? So if we resolve that mathematical term, we find that this is 4s squared times s, which would be s cubed, which would be 4s cubed. So this is equal to 4s cubed. Now all we have to do is solve for s. And if we do that, and I did it correctly, the molar solubility is 1.4 times 10 to the minus 8 moles of this compound per liter. Okay? And that would be C. Any questions? So what you can do is, once you set up your equilibrium expression and you know how many ions are produced from the compound, then you choose your S equal to whatever this is going into solution. Then if there's one of these that went into solution, that would produce one of these, so that would be S. And in this case, it produces two of those, so that makes two S's here. So let's see. I'd like to try just do another one. What's the KSP for silver chloride? Here it is. Let's do silver chloride. This one doesn't have a number. I'm just making this one up to follow from that one. Um, 1.57 times 10 to the minus 10. And this would be no number. So this compound would produce one silver ion with a 1+ charge and one chloride ion with a 1- charge. So we can write our expression as, if this is S, minus S from this side produces one here and one here. So that would be S times S, which would be S squared, which is equal to this. And then we would just say S is the square root of 1.57 times 10 to the minus 10, whatever that happens to be. So that would give you the molar solubility of silver chloride in water. There are no common ions in the solution to begin with. That's another stipulation for using this method, that there's nothing else in the solution, because this KSP is valid no matter what the solution is. But if you have other ions in solution, then you have to take those into account, and that's where you have to use the ice table. But if you only have pure water, then this works fine and quick. Okay? So now we can go back to our numbered problems. Let's see. Okay. This was fairly simple. Should do this one really quick. What are we given? The compound is barium fluoride. Right. We dissolve it in water. So what does it produce? It produces a barium ion plus 2 fluorides. Okay. And it says that 7.5 millimoles, 7.5 millimoles dissolve at equilibrium, dissolve in 1 liter. All right. So that tells us what the solubility is. That's equal to S. And the question is, what's the KSP? Well, the KSP would be calculated from the barium ion concentration times the fluoride ion concentration squared. We just need to resolve this into a value for S that we can put in here, because one of these produces one of those and two of these. But the kicker is this millimoles. So how do we get molar out of this? If we're going to calculate molar solubility, we need to produce a molar value for S. There are two ways you can do it. You can convert millimoles to moles, and in that case, moles would be divided by 1 liter, so that would automatically be the molarity. That seems to be the easiest way. So how many moles is 7.5 millimoles? Well, a milli is 10 to the minus third of anything. So you just say 7.50 times 10 to the minus third moles per liter. So there's your molarity, 10 to the minus third. That's equal to S. So we need one S in here and two S's in here. So we would just calculate 7.5 times 10 to the minus third and 2 times 7.5 times 10 to the minus third, 2 times squared. Okay? I could cheat and look at my sheet, but I want to do it longhand just to be sure. 7.5 10 to the minus third, and this is going to be 1, 2, 3. Actually, it's to the third power. Here it is. And then times 2. So I get 8.4 times 10 to the minus 7. Let's see, is that 1? I did something wrong. What did I do wrong? Ah, I know what I did wrong. I didn't square my 2. So let's do that first. 7.5 exponent 3 and times 2. There's Heather. Okay. Now we're missing is Kessa. Okay, we're on problem number 2. So I'm just resolving this, because this is equal to S here, ratio of 1 to 1, and this is 2S, because you get 2 for every one of these lost. So I need 2 times this one, which I have to do it again. 7.5 exponent 3. Okay, now 2 times that one and square it. Okay, and then times this one. That's better. So that is C. Okay. Let me see. Let me move this out of the way. It's not bothering you guys, but it's in my way. There. Now I can see Steffi. I couldn't. You were behind my participants plaque. Okay, that's number 2. Now let's take a look at number 3 and see if it's different. These problems are all revolving around the solubility product expression. So that means you've got to write the equation for the solubility in order to work 1, 2, and probably 3. Well, actually, 3 is sort of a... Well, it never hurts to repeat a procedure. So we'll go ahead and do 3. In this case, we're given the solubility of cadmium hydroxide, which is a solid, and it produces 1 cadmium with what charge? Has to be 2+, right? Right, cadmium is, where is it? It is, it's under zinc. Cadmium 2+. Time out for an accident. Close quarters. Okay. I think my drink needs to go on the floor, along with half of it that's already on the floor. Okay. Got most of it. Now back to business. Okay, so we got cadmium hydroxide dissociates in solution into cadmium ion, that, and then 2 hydroxyls. 2 hydroxyls. Okay. All right, what else are we given? We're given the solubility, right? So the solubility is 1.67 times 10 to the minus 5 molar. So if we let solubility be S, how much of this disappears, then it shows up over here as the same amount on this side. That means that's S. Squared, right? So if this is S, that means that one is here, and 2 times that one is here. Squared. Okay? So you do the math, right? 2 is squared, 1.67 times 10 to the minus 5th is squared, then times that one again. And we should end up with 1.86 times 10 to the 14. Okay? That was 3. I think it's time I made some more room up here. Yeah. All right, let's see if this one's different. This one's okay. Let's do 4. 4 and 5 are similar, so we'll just do 4. All right, we're given this imaginary salt, M3Z2. It's a solid, and it dissociates how? Well, it's going to produce 3 of these, right? And 2 of those for every one of these dissociated. Let's deduce the charge, right? If these are neutral, then, and if you remember back from Gen Chem 1, the best way to handle a salt formed from an odd charge and an even charge is just to cross multiply. So this would have been produced by a 2 here and a 3 there, right? 3, 2. So that means this should be 2 plus, because it's first, right? Cation's always first. So it's got to be a plus, and 3 minus. Okay? So now what else are we given? We're given the solubility, 3.1 times 10 to the minus 7. Okay. So we just need to write an expression for that. Well, while we're here, if one of these dissociates, how many of those does it produce? 3 of these, right? So we're going to show up with 3 S's on that side for every one of these, and 2 S's for every one of those. So now we can say KSP is equal to this expression cubed times the anion squared, and then we just substitute in the values. 3 times this value cubed, and 2 times that value squared. Then all we have to do is multiply that times that, square it, multiply that times that, cube it, then multiply them together, and we should get as our KSP. Okay? What could these 2 possibly be if they were just elements? Let's see, 2 pluses. Well, those could be one of the alkaline earths, or it could be one of the transition metals in that particular oxidation state. This one could be 3 minus. Okay, 3 minus, what would that be? That could be something in the pnictogens, in the nitrogen family, right? Because halogens, halogens are -1, chalcogens are -2, pnictogens are -3 when they're by themselves. Now, if it was a polyatomic ion, my guess would be phosphates. PO4 3- is notorious for forming insoluble compounds. Just side note. Okay. So we can skip 5. There she is. NASA's here. Okay, I'm going to repeat myself because we were missing a couple in the very beginning. For Chem104, your labs, if you have submitted something and you haven't in Blackboard and you don't see a grade for it yet, that means it never showed up on my side because I've graded everything that showed up. So if you look in your My Grades and you think you've submitted something and you don't see a grade return for it from me, then you probably should attach it to an email and send it to me. And then I'll manually put it into your My Grades so you'll see it then. All right, let's see. Where was I? Okay, number 6. Now we're getting into common ion effect on solubility. So here we have with number 6, we're given an initial concentration of, well, let's write the solubility expression first for cesium iodate. Okay, cesium, the iodate polyatomic ion, solid, and then it yields cesium. What's the charge? Well, you have to know that iodate is a -1. So that means this has to be 3+. And then the iodate ion, let me redo that. I want to make room so that we can set up an ice table underneath it. So let me squeeze this one over a little bit more. There we go. Now we can put cesium right next to 3 iodates. There we go. Now, that's our solubility expression. But we're given okay. No, I'm sorry, this is not a common ion experiment. This is just solubilizing this compound in water, but instead of asking for the solubility, we're asking what's the concentration of that ion. All right. So if we're given the solubility, no, we are asked for the KSP. All right. So the KSP would be calculated as this. 1 times this. There. And what are we given? We're given the concentration of this iodate ion in the saturated solution, which means this is in equilibrium with that. So if the concentration here is 5.93 times 10 to the -3 molar, that we can easily go, this goes in here unaltered because this is the concentration of that. We don't have to multiply it times 3. We do have to keep the power, but instead of coming from this side where we have an S value, and this would be 3S, that is 3S. Okay? So in order to calculate this, we need to know what that is. So if this is S, what would it be equal to? Well, S then would be 1/3 of this. If that's 3s, then this is a third of that value. Right? So now we can put in this value divided by 3, and then this value cubed. Now we can calculate the KSP. And that should be we just cube this one, take a third of that one and multiply it by that one, and you get that value. So this is an example where suppose you were given the solubility of that compound, and instead of making S equal to that, you made S equal to that. Then that's the kind of complication that you would experience in doing your calculations by choosing the wrong S value. But in this case, we didn't have a choice. It was given to us. So we had to deduce what the other one was from that value. This is equal to 3s. So this 1s has to be a third of that. All right. Sooner or later, we're going to get to a common ion problem. And then we do have to use the ICE table. Seven's another, we've already done one of those. Let's see. If number 11. All right, we can do number 11. We got time. And then we'll move from there into take a different tack. So we're given the solubility of silver phosphate. Now, what if that problem had read the solubility of silver phosphate at 25 degrees is that value? What would you do then? You're not given the formula for silver phosphate. You have to figure it out, right? We know that silver is always +1. And phosphate is a polyatomic ion that's always 3-. Right? So that means we have 3 of these, and 1 of those. Okay. So that will give us 3 of these, aqueous, and 1 of these, aqueous. And then what else are we given? The solubility, 1.5, so S equals 1.55 times 10 to the minus 5 molar. So that's how much of this goes into solution in pure water. So what does it produce on the other side? Because the question is, what's the concentration of this? Right? So we need to know the equilibrium expression. You know, we don't need to do the equilibrium expression. You probably saw that coming. Why? Because we're given the solubility at equilibrium. So if this much goes into solution, how much of that does it produce? It just produces 3 of them, right? Right? 15, 16, 4 times 10 to the minus 5. That's why this one is C. I was almost made it more complicated than it really is. All right. So that was 11. Now let's shift gears just a little bit. And compare the solubility products of these compounds and find out which is the most soluble. All right, so I'm going to go ahead and write them up here so I can talk about them. Barium sulfate, cobalt sulfide, lead 2 sulfate, silver bromide, and barium carbonate. And we have KSP values for each one. This one is 1.5 times 10 to the minus 9, 5 times 10 to the minus 22, times 10 to the minus 8, 10 to the minus 13, 6 times 10 to the minus 9. Okay. Now, under what circumstances can we make direct comparisons with the KSP? If every compound produces the same number of ions in solution, then we can do a direct comparison of the KSP. If they produce different numbers of ions, then we have to actually solve for the solubility in order to compare them. Look, this one produces one of these and one of those. 1 and 1, 1 and 1, 1 and 1, 1 and 1. So that's good, especially on a test. Because now you can just look at these numbers and say the most soluble one is the one with the largest KSP, which would be this one. Right? ABC. Okay? Now, if I'm nasty on a test, I would give you different compounds that form different numbers of ions. Then you'd have to go through and calculate the solubility for every one. That would not be nice. Okay, that was number 12. By the way, the reason you can say all of those KSPs are comparisons is for the solubility product, for the solubility, you would have S squared. For all those compounds, it's just S squared. Okay. That was number 12. Now, number 13 is one of those bad ones where you have to do the comparison. I guess we could go through that. Why don't we save 13, and if we have time at the end, we'll come back to it. But what you would do is go in and solve for every solubility, then you can make the comparison. But let's go through and look for, okay, 14 is a common ion situation. Here we go. Now, here's our first one. All right. So, the KSP for a salt in aqueous solution is constant. It's always the same. The solubility may change depending on the environment. So if you're given a pre-existing and initial concentration of one of the ions that is produced by the dissolution of your salt, then you have to go in and set up your ice table. So we're given the KSP for silver iodide. What does silver iodide do? Solid produces this and this. Here we go. And the KSP, I'll put it way down here, for silver iodide is 1.5 times 10 to the minus 16. Now, initial change, equilibrium, and we're given the KSP, plus the initial concentration actually, it says that the solution is 0.3 molar sodium iodide. Okay, so what does sodium iodide do in solution? All sodium salts are soluble. So it produces nothing but this and that in solution. Well, you look at what can sodium react with. Well, the only thing it can react with is with iodine, and we already showed that it doesn't form a solid. It's a spectator. So this is the one we're concerned with. That concentration is the same as this one because 1 to 1, 1 to 1, that's the same concentration here. So now we can put the initial concentration here as 0, and here is actually 0.30 molar. That's our starting point. Now what happens? Well, we're going to take some of this, we're going to lose one of these, and it's going to show up as one of those and one of those. Okay? So now, this is not part of the expression, so we don't have to deal with that. But we do want to focus on these, because they're over here as this and this. Okay? So we have S and S plus 0.30. So this expression would be S and S plus 0.30 would be this times 10 to the minus 16. Okay, now we just have to solve for S. The question is, how do we do that? Well, we're going to end up with S times S is S squared, and then S, so we're looking at a quadratic. So let's see. Look at this value right here, 10 to the minus 16. Even in pure water, it's not going to produce a whole lot of iodide. But if there's a competing ion in there, an iodide ion, it's going to produce even less iodine. So I think it's safe to say that this S, we can approximate that by dropping that one out, and now we have 0.30 times S, and then we just solve for S, which would be this divided by 0.3. Yeah. So 0.3 into 1.5 is what? Well, you divide, it's like 0.3 into 1.5 is like 3 into 15, which would be 5. So our S then would be 5 times 10 to the minus 16. And that would be 14 E. Okay. Now, you can go ahead and solve it for the 5% rule if you want. But if you look at this value, S is significantly smaller than 0.3. That's easy to see. So we're safe. We're much, much lower than 5%. Okay, that was 14. Let's see, let's find one that's different. 15 is very similar to that one. Ooh, this could spin your head around. All right, 16. This is a thought experiment, sort of. So what are we given? We have two salts. They have very similar solubilities in water. The silver salt, that's this one, and this one. Okay. So what do they produce? In solution, they produce one of these and one of those. There we go. All right. They have very similar solubilities in water. Okay, so if their solubilities are similar in water, then their KSPs are similar. But the other part of this problem is that this one is more soluble in acid. So concentration of this in acid is greater than this one in acid. Let's see. Let me be sure that's what it said. This one's more soluble in acid. Yes. Okay, so the concentration of this one in solubility in acid is greater than that one. Okay, what can we say about the relative strengths of these acids? What's the relationship of this one to this one, strength-wise? All right, so let's work backwards. What do these produce? Well, when they dissociate in solution, they produce some of these. Well, actually, this is what we focus on to begin with, because we want to say, how does this react with that and that? So if they're both strong acids, then the hydrogen does not interact with either one of those. If that were the case, if they were both strong acids, then this would not be true. But if this one is more soluble in acid, that means that the hydrogen ion interacts with this one much more strongly to remove that from solution and drive the reaction that way, right? So if this reaction is stronger toward producing that one, like that, versus this one, this reaction favors that direction. Does everybody see that? Okay. If this reaction is favored, that means this is a weaker acid than that one, because it wants to be here, not there. So this one is weaker than that one. Let's see, did I get it right? Y is stronger than X, yeah. So the key to this problem is recognizing what reaction occurs. Hydrogen ions with that one, hydrogen ions with that one, produces an acid. And then you look to this to tell you something about the solubility. Solubility is driven farther to the right with acid on this one. That means that this one has to favor a reaction that removes that one from solution. Okay, 16. Let's see. Let's go ahead and do 17. It's kind of on the coattails of 16 and 17. So what's the relationship between the solubility of silver chloride in water versus silver chloride in strong acid? Okay, in strong acid, we have to consider the reaction that produces the ions. Okay? So, in strong acid, we're going to produce exclusively those ions. Now, it didn't say what X was, it just said strong acid. So we can assume that this one's a spectator, and we only need to focus on that one. So if this is a target-rich environment in protons, then what kind of reaction are we going to get? Well, what can it react with? It can only react with chloride. So hydrogen and chloride, they don't form anything, right? Because hydrogen chloride in solution is a strong acid. So the effect on the solubility of these two, I think that was the question. Yeah, the solubility. They're equal. There's no difference. Right? At the end of the chapter discussion last Thursday, we sort of made a decision tree, kind of. What do you do if you've got a salt where the anion is a weak base? It's a weak base. It doesn't want protons. Right? So a weak base that doesn't want protons solubility cannot be changed by the addition of acid, because it doesn't want the protons anyway. So you're not going to influence the equilibrium. So what do you do then? Well, if you can't attack the anion, you attack the cation. And that's where the complex ions come in. Then if you can form a complex ion with the cation, removing it from solution, then you increase the solubility. So that's the juxtaposition of those two. You look at the anion first and say, is it a strong base or a weak base? If it's a weak base, you can't affect it. So you go to the cation. If it's a strong base, then you can add acid, remove it from solution, and get better solubility. All right, that's 17. Let's see, is 18 worth looking at? Oh yeah, follow right on the heels of my discussion. 18. So we have these different salts. And the question is, which of the following salts is more soluble in 1 molar acid than it is in pure water? Yeah, they put it this way, protons. This is actually pretty simple. I mean, you could approach it from two directions. You can't change the solubility of sodium chloride because it's soluble in water. Right? So you're not going to make it any more soluble than it already is. Same thing with potassium chloride. It's completely soluble in water. Potassium nitrate, potassium salts, nitrate salts, they're all soluble in water. So the real key is look at the difference between these two. And we just looked at silver chloride. Chloride ion is a weak base. It doesn't want that proton, right? So that only leaves this one. You will increase the solubility of iron 3 phosphate in solution because this 3- ion forms, actually it's a big arrow this way, HPO4, 2-. And that removes it from the solubility expression of this one, right, which produces that. Right. So this solubility expression here is influenced by a coupled reaction in which you add protons and you remove this one here. Add protons to this one to make that right there. And then actually, this one goes even further. One minus. Okay, so iron 3 phosphate is the one that is more soluble when you add acid than it is in pure water. Okay, that was 18. Let's see. Okay, 20 looks like it could be brain teaser. All right. Oh, now they're asking for determine the ion product. Okay, so this is fairly simple. We just got to put things up here on the board, extract them from the word problem, so it makes sense of the numbers. So we've got two reactions here that we're dealing with. Actually, it's presented as two reactions, but we're going to find that really the one that matters is only one reaction. Let's start off with what we're given. Lead 2 nitrate. Okay. All nitrates are soluble, so that produces lead 2 plus and 2 nitrates in aqueous solution. And the problem says that this solution, we add this much of this concentration into solution. And we combine that with sodium chloride. So these are both soluble salts, because that's a nitrate and this is a chloride and a sodium salt. They're all soluble. So you're going to produce this and this. Everything from here goes that way, everything from here goes that way. So what do we have for sodium chloride? We have 2 times 10 to the minus 10 squared milliliters of 0.020 molar sodium chloride. Now it tells us what the KSP is, but it asks you for the ion product. So the KSP, you don't need it, right? We're looking for Q, not K. So what's going to happen? Well, all of this ends up over there, all this ends up over there. So we need to say, what happens over here? Well, this cation and that anion are soluble, completely soluble. So there's no reaction there. So we're concerned with this one and that one. So really what we want is this reaction. Well, that's not right. We're going to write it as a solubility product. So that means we need the anions on this side all right. Well, what are they going to produce, right? That's a 1 minus and this is a 2 plus. So it's going to take 2 of those. And then backwards we have this and that. Right? As it turns out, lead 2 chloride would be insoluble. If you look at your, let's see, did I put one of those in here? No. Oh, well, we can tell that's where the KSP comes in. The KSP for this, for the lead chloride, actually they told you what you're looking for, lead chloride, 1.6 times 10 to the minus 5. So that means this is your insoluble salt, or slightly soluble salt. So we don't actually need the number after we determined that this is the insoluble part. Then the Q is calculated from that value and this value there. So what's the lead concentration going to be? Well, we have this many milliliters and that many moles. So if we multiply those two together, we get so many millimoles, right? So I get 2.24 times 10 to the squared millimoles of lead 2 plus. Okay, so what's the volume? Right, we need concentration. Remember, millimoles divided by milliliters is molarity, because the millis cancel out. So we just need total volume. So what's the total volume? Well, it's 2 plus 3.5 times 10 to the minus 2. So that's 5.5. Excuse me, 10, not minus 2, 10 squared. Milliliters. Right. So there's your concentration for lead 2 plus. For sodium, we have 0.02 times 2 squared, 2 times 10 squared, and then 0.02. So this gives us 4 times nothing. It's just 4. And it's in the same volume. Millimoles per milliliter. Right. So we get a value there. Now, we know the concentration of our chloride, right, because it's 1 to 1. And we know the concentration of our lead 2 plus. So we just plug this number in here and square it. Plug this number in here times that, and we get a Q value, which should be -4. All right. Now, the question that's not part of this problem number is, will you get any lead 2 chloride precipitating? Is it going to drop out of solution? Any of it? So what we need to know is what's the K value. So if you know the K value, which is 1.6 times 10 to the minus 6, what can we say about that precipitation? Is there going to be some? Yeah. If the Q is greater than the K, you get precipitation, because the Q tells you that you've got more on this side of that expression over here than you can hold in saturated solution. That says Q is bigger than K, so it's going to send some of it back this direction. So you will get a precipitate out of that, from that Q value. Okay, that was 20. Let's see how many we got to go. Got less than an hour left. So I better pick up the pace a little bit. Okay, we've done solubilities and solubility products. We've done common ions. We've looked at Q values. And seen how the Q tells you whether you'll get a precipitate or not. So 21 is another one of that type of problem. 22 compares precipitation of these solutions where you have a combination of several metal ions and you're trying to remove one of them as the salt, the chloride salt. So let's take a quick look at that one, because that speaks to the issue of well, actually, 22 is simpler than you might suspect, because copper chloride, silver chloride, and gold chloride all produce the same number of ions in solution. So we can do a direct comparison of their KSPs and tell you which one's going to precipitate first as you titrate with chloride ion. So the KSP for, let's see, copper, silver, gold, yeah, they're in order. This is 10 to the minus 7th, this is 10 to the minus 10, and this is 10 to the minus 13. So this is the least soluble, and as you add chloride ions, that one comes out first. Okay. Now, if we had, it's another case, if you actually had different ions produced from them, then you would have to determine their solubilities. And then you could compare which one would come out first. The one with that's least soluble would come out first. So if you had multiple anions, say, with a cation, then it would just make the problem a little lengthier, more complicated, but you'd still have to determine the solubility in order to make this assessment. All right. '24 should be fairly easy, because with 24 you have the decision tree, right, for sequential precipitation of metals. And in the qualitative analysis scheme that's given in that table, how are the analytical group 1 cations separated from others? So you want group 1 separated. Right. So that's at the very beginning, isn't it? Right. So how do you separate group 1s? Well, you acidify the solution. Right. And when you acidify, well, actually, the key is not the acid. The key is the chloride. So all chloride salts will come out, like silver chloride or lead 2+ chloride, or what's another one? Mercury 1. Okay? So those would be separated from all the rest. All right, that was 24. Let's see. Well, 25 is another part of the scheme. All right. So since you didn't have to memorize it, you do have to access the schematic, and that will be in the folder with the exam. So you just have to have it available. Let's see, where was I? Here we go. our analytical group 3 separated from the following groups 4 and 5. So we want 3 separated from 4 and 5. So actually you just look and say, where's analytical group 3? All right. So there's group 1, there's 2, there's 3 separated from these 2. So what do you do to separate these from those? Well, you've already separated everything else from these 2, from everything below it, by adding the base. So to get to this point, you added the base. But to separate these 2, you have to add sodium carbonate. No, that's wrong. Because to get these 3 to come out, you added hydroxyls. Right? So when you added hydroxyls, these dropped out, and that separated them from the rest of them. Okay, so I was jumping ahead of myself. Let's see, that was 25. Let's see, prior to that one, okay, that's true. But what happened before this? Well, we already had that in solution. So when we added this, that made more of this available, which dropped out the third group. That's why the answer D says you added this, which was in a previous step, and then the basic solution. Okay, does that make sense? I went around the barn about 3 times to get there, but up to this point you had added hydrogen sulfide, and then when you added hydroxyls, excess base, then you caused these to drop out, and that's separated from those. So it's a matter of wording. All right. That was 25, which was a little tricky due to the wording. Let's see if there's anything to be gained from the next one. Okay. Number 26. That looks to me like we're into Hess's law. Yeah. This will be a good exercise. 26. Okay, we're given these equilibrium expressions. Copper 2 plus in solution, and hydroxyl. Okay. And then the KSP for this one is 1.6 times 10 to the minus 19. And then we're going to combine that reaction with this one. Okay. And there. And the K for that reaction. Actually, this is a complex ion. So, well, the formation constant would be going this direction. So that's why they just call this one K. Because if they said K sub F, it would imply that the reaction was reversed. 1.0 times 10 to the minus 13. Okay, so now what we're looking for is what's the equilibrium constant for this equation? Here. And we form that. Aqueous plus hydroxyls. Okay. So what's the equilibrium constant for that? If we use Hess's law and combine these, we look at the target equation and the component equations and see if any modifications have to be made. All right, so this one's on the left-hand side, that one's on the left-hand side in the proper amounts. That's good. This one's on the wrong side over here. So that equation would have to be inverted. So if we, let's see, how would I do that? If I invert that equation, put this on the other side, what would that do to this value? Well, the K value is just the inversion. If you flip the equation that way, the K is the inverse of that reaction. So what would the inverse of that one be? Just 1 times 10 to the minus 13 divided into 1. And you have an inverse key on your calculator. Oh, duh. There you go. You just change the sign of your exponent because that's 1. So this is the one for that. So now what happens when this one comes over here on that side? It cancels. That's why you don't have copper ions down here. But you still have hydroxyls. And the ammonia goes over here. And this complex ion goes over here. So now with that inverse, we've got the right numbers of everything. We just need to combine these two. So what do you do when you combine equations? What happens to their K expressions? You multiply them. So we multiply this one times this one. So KSP times the inverse of that K is equal to this one times that one. Something went wrong. Let's go back. Start all over again. That one times that one. Hey, my calculator batteries are running low. Yeah. All right. Let's see if I can do this in my head. So it'd be 1 times 1.6. 1.6. And then 10 to the 13th times 10 to the minus 19th, we combine the exponents. 13 positive, 19 negative leaves us with minus 6, right? So that should be our K for the combined equation, and let's see if I did it right. 26. Yep, there it is. Okay. I think I need to change batteries. It won't even shut off. Okay. So much for that. Oh, maybe it's all that. Maybe I spilled some Coke on it. That's not good. I bet that's it. I messed it up. Deal with that later. That was 26. So we're starting to dip our toes into complex ions. Let's see. All right, we've got a few here. How do you calculate the molar solubility of these compounds? So we've already done silver chloride before. Let's see. Iron 3 hydroxide. Let's do that one. Iron 3 hydroxide, right? Hydroxide 3. Aqueous, aqueous. If solubility is here, then this would be one of those, and this would be 3 of those, right? Then the solubility product would be this times that to the 3rd power. Okay? So 3 to the 3rd power is 27, right? 27. That's cubed times another one is s to the 4th. So 28 would be E. Okay, that's how you do that. Quick, fast, and in a hurry. You do have to start from the solubility expression, because unless you're good at visualizing these things in your head, putting them down on paper keeps you from making mistakes. It keeps me from making mistakes. How about, oh, this is a good one, 30. I wouldn't want to try this one in my head. Calcium phosphate, right? You're just given the name, calcium phosphate. You know there's calcium and there's phosphate. This is a 3 minus, that's a 2 plus. So this is going to be 2 here and 3 there. Now we can do 3 calciums, right? And 2 phosphates. Now, if this is S, how many of these are produced? 3 S's, right? Solubility comes from this side. 3 S's here and 2 S's there. So now the KSP is 3 of these S's cubed and 2 of these S's squared, right? So that would be 4 times 27, 108. 108, that would be S cubed and S squared would be S to the 5th. Let's see. Yep. See. Okay. All right. Let's see. Here we go. "31 takes a few extra steps." Let's hold that one. We'll come back to it. Ooh, 32 is a good one too. Let me look ahead and be sure that I'm not missing something. So I want to be sure and get everything covered. Okay, we need to do 43 also. And last page. "45. Maybe 46. So now let's, yeah, I'll go back to 31. I think we got time to do those last few problems. Okay, the solubility of calcium sulfate. Calcium sulfate in pure water produces calcium and sulfate ions 1.14 grams per liter. 1.14 grams per liter at 0 degrees. Okay, that's all we're given. And then the question is, what's the solubility product? So the solubility product is going to be this. Right there. So we're given this. So what is this? This is S, but it's in the wrong units. So we need to convert that to moles per liter. So let me get rid of that thing so we can do a dimensional analysis. Right, if we do that, that gives us moles per liter. So we just need the molar mass of calcium sulfate. Right. So since my calculator is busted, I'm going to have to go back to the cheat sheet. Let's see, 31. The molar mass of calcium sulfate is 136.14. 136.14. So divide this into that, and we get 8.374 times 10 to the minus third molar. And that's equal to S. Right? So the ratio is one of these, one of those, one of those. So that's S and that's S. So it would just be S squared, which would be equal to this. Squared is equal to your KSP. And that should be 10 to the minus 5. Okay, so that was the trick to that one, is just the unit conversion. All right. Let's see, which did I circle next? 43. Okay, what's the maximum concentration of iodide ions that will precipitate silver iodide, but not lead to iodide, from a solution that is 1.5 times 10 to the minus third molar each in silver and lead? Okay, and it gives you the KSPs for each reaction. All right, so we're dealing with these two reactions. All right, and the KSP for this one is that is equal to 1.5 times 10 to the minus 16 versus lead 2 iodide. So it produces lead 2 plus and 2 iodides. And the KSP for this one is that. And squared. And that value is 10 to the minus 8. Okay. So what else are we given? Nothing. The question is, what's the maximum concentration of iodide ions that will precipitate this one and not that one? So we're looking for the maximum iodide concentration to yield this, not that. Let's see, this should be 2. Yeah. All right. So the maximum concentration that you can put of iodide that you can put into solution is not related to this, it's related to that. You want to know how much of this you can have in solution without making that. So in that case, the Q is for this reaction equal to that value. Right, so you want this Q value to be equal to that. Because anything greater than that, if you increase that just a smidge, then the Q would be greater than this and start precipitating that. So the target is this equation, and what can you get away with? What's the maximum Q value that you can get, and it's that. All right, so we still do have to go back to this one because we need a starting point. All right, so I'm going to have to make some room here. In fact, I'm going to have to erase that and bring it back to us later. Okay. So we need our ice table, and we need to know the starting point. The initial values are what we're going to draw, because this reaction, we don't want this reaction to take place, but we have to know what is the starting point. So the starting point is derived from this one. Okay. So if this value is given to us, then at what point, let's see, where am I think I've left out some information, 43. Yeah. So the starting values here are 1.5 times 10 to the minus third molar. 1.5 times 10 to the minus 3 molar. And also this one, right? This one is also 1.5 times 10 to the minus 3 molar. So at what point, we need a starting point for this one also. And the starting point is determined by, what would that be? Right? If we put this in here and that and solve for this, that would be our starting point for here, because that's the maximum amount that you can get that one to precipitate silver without precipitating this one. So we need to plug this one in here. That one is the K, and solve for this one. And that solution gives us 1 times 10 to the minus 13. So there's our starting point. We derived our starting point for this reaction from that reaction, because we know this value here, we know this value here. We calculated this one. So this is our starting point. Now, what's the change? Well, the change is how much of this iodide can we, well, we're not going to have any change here, but we are going to have an addition of X here, because this X is external. It's not derived from that one yet. It's derived from this one. So how much more can we add and still be at equilibrium? All right. Okay. So in this case, instead of eliminating the X, we're going to eliminate 10 to the minus 13th, because it's so much smaller than X could possibly be. So that means our expression, KSP, actually our Q, is this one. And this one is going to drop out. And now all we have, no, excuse me, that stays. This one drops out. Now we have X, and our expression then is squared. So the X concentration of I, and we solve for I here. Right? So that's equal to, what is it? 10 to the minus 8. And then once we solve for x, we should get 3 molar. So if you want to verify this to be true, you need to insert the x into the expression, because we already know what these starting places are. And, well, let me see, what was the question? Maximum concentration of iodine that will precipitate silver iodide. Okay. Technically speaking, the concentration of iodide would be this one plus that one, right? But that's so small compared to this, you might as well throw that one out. So in this case, X is the answer. 10 to the minus third molar is the most iodide you can have in solution, precipitating this one without precipitating that one. Now, why did we have to go to all this trouble? Because of the separation of these two reactions in terms of their K values, right? The K value for this one is 10 to the minus 16. The K value for this one is 10 to the minus 8. So there would be a wider separation if this were 10 to the minus 5 or 10 to the minus 3. Then we would have a larger margin in here that would be available before you get precipitation of this one. Okay, and in fact, the greater the separation between the K values, the easier it is and the purer the separation is when you try to separate one of these from one of those. If the K values are very close to each other, then you get cross-contamination. But if the K values are very far separated in orders of magnitude, like minus 16 versus minus 8, that's a big separation. Then you can have this extra iodide in there, and that assures the precipitation of this one before you get to that one. So that means you will have a very pure silver product derived from that solution, as long as these K values are widely separated. Okay? Let's see. What else did I circle? 45. Okay, 45. It's trying to twist on me. Yeah, we got just enough time to do this one. Okay, what does 45 say? The Kf for the complex. So the Kf first is this value, silver. Oh, wait a minute. Getting ahead of myself. The Kf is 1.7 times 10 to the 7th for this reaction, where you get silver and ammonia. So we need 2 of them. We need, yeah, that's right. And that yields this complex ion. There we go. And everything's still in solution. But what this tells us is that is favored by a huge amount. Okay, the KSP for silver iodide, that we just looked at a minute ago, KSP is equal to 1.5 times 10 to the minus 16. What's the molar solubility of silver iodide in a solution that is 2 molar in ammonia? So if we make this 2 molar, what we want to know is what's that? What's the solubility of that in this solution? All right. The simplest way to approach this is to derive, since these reactions are coupled, we want to derive an equation derive an equation where we get ammonia combining with silver iodide, because silver iodide, S for this, is going to be our solution. So we got to keep that one in the final equation. We can get rid of the silver ion because it's on both sides. And they're arranged so that silver and ammonia are on the right side. And then on the product side, we have the complex ion and the leftover iodide ions. Okay, so we need to combine these two equations and derive an equilibrium constant for those equations. So we're going to get, this one's going to cancel, right, because it's on either side. Now we're going to get silver iodide plus 2 ammonias is in equilibrium with silver ammonia complex ion and iodide. Okay. So the K value for this is going to be this one times that one. Okay. That one times that one yields the K for this experiment. So that K is 2.55 times 10 to the minus 9. There we go. So now what we need is set up our ice table. We don't need anything for this, but the solubility needs to be in such a proportion that when we solve the equation, we get the answer that is the solubility. So we can't make this one equal to S. We need to make that one equal to S because it's 1 silver, 1 silver. So this needs to be, well, we're starting off with 0 here and 0 there, and this is 2 molar. I'm getting ahead of myself. Now the change is going to be, we're going to produce some of that, and we're going to lose, okay, we're going to produce some of that, and then the ratio of 1 to 1, and then we're going to lose 2 of these, right? 2 to 1 minus 2. Well, X, make it S. Since this is 1 here and 1 here, then this S is the solubility. There you go. Now, right, there's our equation. This is 2 minus 2S this is S, and this is S. So we need an expression for that value that's equal to this one. All right, I'm going to have to erase some things to do that. Let's see. Yeah, go. We've already used those, so we don't need them anymore. So now that K is going to be equal to, now I better start higher, just in case. Is going to be equal to this one. First power, this one, first power, divided by this one. Second power, okay? And that's equal to this one, this number. Okay, so if we plug in the values, this one is S here. That one is S. This one is 2 minus 2S is equal to 2.55 times 10 to the minus 9. Now the question is, oops, nobody called me on it. We got to square that one. Right, square, square. Now we solve for S, but we don't want to have to use a quadratic. So the question is S going to be a small number compared to 2 molar? Yeah, probably, because you're starting off with a small amount to begin with. And it's probably prudent, if you do eliminate this one, to go back and do your 5% calculation and be sure it's correct. But if we do that, then we have S squared equals 2 times that, which would be what? 5 point, what is this? That's 110 times 10 to the minus 9. Nope. Wrong. Squared. So it's 4 times that. So it'll be 10.2. 10 to the minus 9. And then we do square root of that. And S then would be 1 times 10 to the minus 4 molar. Oh, we don't even have to do the calculation. 5% calculation. Look how small that is. 10 to the minus 4th compared to 2. We're good. Okay, we got about 4 minutes. Is there any we could look at 47. But I'd rather leave it open for questions if we haven't covered something that you thought of in the meantime. Okay. Everybody wonders why I've got stuff stuck up my nose. Nosebleed. Must be the aspirin. The doctor's got me on aspirin. Okay. Any questions about lecture or lab, actually? Either one's fair. I'm leaning toward canceling the last lab, the one electrochemistry lab, because I haven't been able to come up with a good virtual exercise to finish that one. Guys, we'll see you on Thursday.
Okay,
Bye.
everybody have a great day. In case I'll look for your email. Okay, girlfriend?
All right.